All right, yesterday, this is just a standard lab report for this, whereas the synthesis lab is going to be a little bit more involved. So we'll have more time for the synthesis lab, but this lab report will be due next week. All we have to do is answer some questions at the end of the lab. Pre-lab questions, you don't have to have those answered for this, but some of these are helpful. Understand the lab. Sometimes I'll require pre-lab questions or have a pre-lab quiz. I'll let you know if that's the case, but most of this is pretty straightforward. And so here they just want the colors, and we started looking at this yesterday, correct? So what did you get for the color for the copper 2 sulfate solution? Okay, clear blue. So you had a light blue color for this? Okay, so we put light blue. How about the tetramine, copper 2? This is not blue.
Not like dark blue?
Dark blue. After the HCl addition? Was that this one or was that the other one? After the HCl addition, what happened? Okay, so it just went to a very light blue, almost colorless. There could be two factors with that. One, it should switch to light blue, and two, it depends on how much HCl you add. This is why I was saying probably add the 12 molar stuff, the more concentrated, because another factor that's going to happen is dilution. And so if you're adding a lot, it's all the colors are going to lighten, so it's hard to tell if it's a dilution effect or something else. Well, it wasn't supposed to be a dilution effect. What was supposed to happen is this. And so what we do is we draw out the equilibrium. This is the equilibrium. It's between the aqua complex, which is this copper 2. Did I talk about this yesterday? Right. And the amine. And we can control the distribution, that is a population here, population distribution, by either removing some of the reactant. And the way we remove it is we add HCl. We add HCl, it converts the ammonia to ammonium. And so we remove this, which is going to shift it left, or we can add more. If we add more ammonia, then it shifts it right. And so to have a more dramatic effect here, the concentrated ammonia and the concentrated HCl is probably best to use for this particular one. That way we can factor out the dilution, especially since it's going from dark blue to light blue. I mean, there isn't a dramatic change in color there. Although the dark blue is very dark, if you have enough ammonia. When you did add the ammonia, did you get a light blue precipitate also? Well, some people did. I know, like Juan, you got a light blue precipitate sitting at the bottom, yeah. And that's because the ammonia, there's another chemical property of ammonia. Not only is it a Lewis base attacking this, but it's also a Bronsted base. And so ammonia can hydrolyze water to form a little bit of hydroxide, which precipitated out the copper. It's copper 2 hydroxide. The copper 2 hydroxide is light blue. How about the nickel? What did you guys get for nickel 2 chloride? Light green. So this lightens something. You could put in whatever. You don't really have to write a paragraph about what happens. How about the amine complex of nickel? What color was that? Light purple? Okay. And so we go from green to purple. This is maybe more dramatic as far as the color change goes. And then we're going to do the same thing. We're going to have an equilibrium. Let me see if that is this. this is for copper 2 sulfate. So the next part of this lab is I have so many of these open. The cobalt. So, oh, this is cobalt. I guess they don't care about nickel, huh? But nickel would just be the same thing, essentially. So we're just going to continue. So if we were to do nickel, we'd draw out the same kind of diagram reaction. How about the cobalt 2 chloride? What's the color of that? Red. After the addition of HCl? Blue? Dark blue. After addition of water? Pink. Account for these changes for the cobalt solution in terms of Le Chatelier's principle. So for cobalt, we form a chlorido complex for this. And let's take a look at what that is here in the procedure. You know, is it tetra, hexa? And so probably the easiest, and you aren't expected to have this memorized. But over here we have the hexa aqua going with 4 chlorides to form the tetrachlorido cobaltate ion, and then the 6 waters. All right, so cobalt 2 aqueous is also known as this hexa aqua complex, and so these are pretty much the same thing. And then we have 4 chlorides, or chloridos, if you want to call them that. And then we're going to form the tetrachlorido complex. This is cobalt 2 plus, so this is going to be 2 minus. And this can go both ways. So what happened? Did I talk about this yet? What happened? We went from a coordination number of 6 to a coordination number of 4, right? And so what happened to the other 2? The other 2 ligands are still there. This would be the diaqua tetrachlorido, you know, that kind of thing. Typically. But anyway, when we add water, that's going to impact the reactants more than the product here. If we add HCl, that's just going to shift it. And so we could do the HCl. So we add HCl, that's going to increase the chloride. And so increasing chloride, which means we have more reactant. More reactant is going to shift it to the right. So we'll have more forward reaction here. However, when we add water, we end up diluting the whole thing. And so we add H2O. Oops. Everything's diluted. Reactants and products are diluted. But due to the difference in solute species here, the dilution is going to have a larger impact on the reactants than on the product. And what happened to the color when you added water? Well, the color shifted back towards red. One way of thinking about this is which side is more crowded? You know, if you're putting product and reactant in a container and they're in the same container, which is going to take up more space, the reactants or the products? Well, over here, the reactants, we have 5, 1 cation and 4 anions. So we have 5 solute particles in that, in this equilibrium. Over here in the product, we have only 1. And so, you know, which one's going to take up 5? 5 of them are going to take up more space. And so if we make more room, then these can expand out and this can become more favorable. And so dilution is going to have a uneven impact on these because we have more solute. And therefore, the more dilute, that is, the greater the volume we have, that's going to favor the side with more solute. And so the dilution is going to shift it to the left. Because that's the side that will benefit from larger volume. Okay. Now, what are we supposed to do at 10 and 11? Do you know? What we're supposed to fill in there? 10 and 11. So let's go back to the lab and take a look and try to find out. See 1 up here, 1 here, 2 here. Okay, here. It says record the color of the solution on your report sheet, 1. Must be line 1. Record your observation on the report sheet, line 2. Note the color, line 3. Line 4. Oh, here's 11. So we must back up to 10 here. Record your observations on your report sheet, 10. So to half a milliliter, 10 drops of 0.1 molar sodium carbonate in a large clean test tube, add 10 drops of 0.01 molar silver nitrate. So sodium carbonate plus silver nitrate, that's what we do here. And so the reaction here is just a straight metathesis reaction. Sodium carbonate plus silver nitrate. Okay, what does this form? Well, what do you predict this is going to form? This is an AB plus CD. It's going to form what?
It's going to form silver carbonate and nitric acid.
Good. Silver carbonate. Not nitric acid.
Sodium carbonate.
Sodium carbonate, yeah. Or sodium nitrate, sorry.
Nitrate.
Sodium nitrate. Yeah. Silver carbonate's a solid, and it's a white solid. So did you get a white PPT here? And so we should have gotten a white PPT. White precipitate. Let's take a look at number 11. Okay. Cautiously add 6 molar HNO3 dropwise to the test tube until you observe a change in appearance of the contents. So we're going to add nitric acid. To the contents of this. So in the contents of this we have the products silver carbonate and sodium nitrate. So if we add nitric acid to sodium nitrate, we're going to form sodium nitrate and nitric acid. No change. But if we add nitric acid to silver carbonate, what should happen? We should form silver nitrate and hydrogen carbonate. Hydrogen carbonate is called carbonic acid, and we know that carbonic acid is not stable. What does carbonic acid decompose into? CO2 and water. And so did the white precipitate dissolve in nitric acid? Yeah. So white PPT dissolves to form a CCS. Have you heard of a CCS before? Clear colorless solution. Plus, I don't know if you saw this, but you should have effervescence with a CCG, a clear colorless gas, which is CO2. Did you see gas bubbles? No? Yeah, it depends on how much forms. So you may or may not have seen this. All right, that's 11. Let's move on. What are they asking for in 12? To the solution saved from above, add 0.1 molar HCl dropwise until you observe a change in the appearance of the contents of the test tube. Record your observations on your report sheet 12. So they aren't asking us for everything here. To the solution saved from above, add, okay, what was the solution saved from above? Adding acid to this ammoniacal solution will remove the ammonia by forming ammonium. This causes the equilibrium 6 to shift to the left. Okay. And so when you added HCl to that solution, did you see a precipitate form? For number 12. What did you have for that? Well, you should have gotten the white precipitate here. The white precipitate is going to come about because we're looking at this equilibrium, the silver ions plus the 2 ammonias. This is going to yield the diamine silver ion. Silver 1. Now what happens when we add chloride? When we add chloride, what's going to happen is it's going to remove silver. And so plus chloride. And so we're going to remove silver by precipitating it out as the chloride. So this is going to yield AgCl. And what that's going to do is it's going to shift this equilibrium to the left. Essentially, we're removing reactant here by precipitation of AgCl. "13. Did the AgCl dissolve? Explain." So what are they asking at 13 here? While mixing the contents of the test tube, add 15 molar ammonia dropwise until evidence of chemical change occurs. And so what should have happened is this. If you add 15 molar ammonia, what do you expect? Well, if we add ammonia here, we expect it to shift to the right or shift to the left? Actually, I need to do this differently here. What should happen here? If I add my ammonia here, I should shift this to the right. If I shift this one to the right, this one also shifts to the right. And if this one shifts to the, well, actually, this one's not the right one. Sorry, let me. Let me wait for this to recover. Hopefully I didn't lose it. While this word is doing its thing, let me go back to this. We'll look at the test, the key. What is this? Forget it. All right, the number of basic reaction types is 3. What are they? Acid base. Well, Bronsted is part. Acid base actually has 2 subtypes, Bronsted and Lewis. Yeah. And so we have acid base, metathesis, and redox. Those are the 3. There's subtypes like Bronsted, Lewis, etc. Combustion is categorized as a, what type of reaction is combustion? One way to check, sometimes it's difficult to tell, but one way to check if a reaction is redox is all redox reactions will be accompanied by a or accompanied with a change in oxidation state. So in metathesis reactions, the oxidation states never change. In acid-base reactions, the oxidation states do not change, except for Lewis, but we count things funny with Lewis. And so since we count it funny, the oxidation states don't change when it's counted in the way we count it. And so the only type of reaction where we see an oxidation state change is for redox. In combustion reactions, the oxidation states do change. Like, for example, oxygen. Oxygen O2 is 0, but oxygen in CO2 and oxygen in water are -2. Okay, so combustion is categorized as a redox reaction. 3, formation of a precipitate or a gas is the driving force for redox reactions. No, when oxidation states change, that results in a significant change in energy and reactivity. So for example, sodium metal versus sodium ion. Sodium ion is unreactive, stable, whereas sodium metal is extremely reactive and reacts violently with things like water. You don't have changes in oxidation states in metathesis and acid-base. And so we look for little things. Little things would be like precipitation or gas formation. Gas formation is always favorable because gas formation, we expect the entropy to be going up. But then we have to look at the energetics. And if the energetics are very, very unfavorable, then the reaction is not going to happen. And changes in oxidation states involve much larger magnitudes of energy than precipitation and the others. So formation of gas could help. Formation of precipitate could help, but it's not enough. We need something more. And that something more is going from stronger to weaker oxidizer and stronger to weaker reducer. 4, single replacement is categorized as a redox reaction. 5, which is the stronger acid, HCl or HI? This has to do with what effect? Leveling effect. So this is just a leveling effect. They're going to be equal in water. They're both in water, aqueous. Which is the strongest oxidizer below? Isn't fluorine the strongest on the table? Yeah. Fluorine's the strongest on the table, so why isn't it A? Yeah, that's fluoride. Do you see there's a huge difference in energy between fluorine and fluoride? People put fluoride in their toothpaste. And they don't worry about the danger. Well, there are some people who are concerned about fluoride, but you would never put fluorine in your toothpaste. You would never want to be around fluorine. Fluorine's extremely unstable, and whereas fluoride's pretty stable, And so that's part of the issue with that. Now, that is a significant energy change. So redox reactions can be much more violent. In redox reactions, we worry about explosions. In a precipitation reaction, do you really worry? Like, I'm going to precipitate out some calcium carbonate, or I'm going to precipitate out some silver chloride. Do you really worry much about an explosion occurring? No. And so the levels of energy are quite different. I'm going to neutralize a strong acid, HCl, with a strong base, sodium hydroxide. Are you going to worry about an explosion? No, but you should worry about some heat. It's exothermic, and so it could generate a lot of heat, but I really wouldn't worry about an explosion. But then you might go, wait, you know, I know nitrate plus H plus, but don't I need 4 H pluses? So if I don't have 4 H plus, I only have 1 H plus. If I don't have 4 H pluses, isn't that going to be a problem? I'm not going to be able to form all the waters I need. And the answer is no. It's not going to be a problem. The reason it's not going to be a problem is because I can get 4 nitric acids, and out of those 4 nitric acids, I'll just use 1 nitrate and 4 H pluses. And so that means 3 of the nitrates will be spectator, which is fine. So we can adjust the ratios. You don't really worry too much about the ratios. You just worry about if you're missing an important ingredient. You know, but if you have it present, then we can adjust the ratios. Number 7, hydrogen peroxide can act as a oxidizer, reducer, or both. Both. How did you determine this? There are 2 ways to determine this. One is look it up in the chart. Hydrogen peroxide occurs on the oxidizer side and it occurs on the reducer side. Now, it's not equally adept at as an oxidizer or as a reducer. It does have a preference, and that preference is as an oxidizer. It's a much stronger oxidizer than it is a reducer. And so normally when people think about hydrogen peroxide, they think it's strong oxidizer. Which one is the stronger base? Ammonia or nitrogen trifluoride? Bases need a lone pair. Both of those have a lone pair. And we want negative charge density because it's got to share some electron. Ammonia is going to have negative charge density on the nitrogen, whereas nitrogen trifluoride has positive charge density here. And so, if this is already at +3, it's not really going to be willing to give up electrons, electron density. But then you might go, well, fluorine has a lot of lone pairs. Why doesn't fluorine donate? What's the reason fluorine doesn't donate?
Because it's very electronegative.
Yeah, it's the most electronegative element in the periodic table. So we don't even consider fluorine donating, just the nitrogen donating. And this nitrogen's not good at donating. Nitrate is considered electron poor. That is true here. And why is it? It's because the oxidation state. What is the oxidation state on nitrogen in nitrate? Can you look at it and just tell me? You want to be at that level where you can just look at it and just tell me. +5. And so you should try to get some more practice so that you can look at compounds and quickly tell. Well, +5, what do you know about nitrogen? What does nitrogen's oxidation state range from? Ranges from +5 to -3. +5 to -3. Nitrate's at one end of the spectrum. Nitrogen's +5. At the opposite end is ammonia. At -3. And so here are two compounds at the opposite end of the redox spectrum for nitrogen. So we expect nitrate to be an oxidizer, and it is a good one. And we expect ammonia to be a good reducer. This is electron rich. Ammonia is not on our chart though. Which is a stronger Lewis base, sulfide or oxide? Well, unfortunately, our chart up there is not for Lewis bases. Our chart up there is for, or the chart I handed out is not for Lewis bases. The chart I handed out is for Bronsted bases. Yeah. If this question were which is a stronger Bronsted base, then it would be easy. Which one's the stronger Bronsted base? Oxide or sulfide? Oxide. We don't really have to look at the chart. You can tell by the what we call the negative charge density. Which one's a bigger ion? Which one's a smaller ion? Oxygen is smaller. They both have the same charge, so oxide is going to be a stronger base. That's Bronsted, but for Lewis, we have to look at what it's reacting with. Do you guys remember what HSAB stands for? Anybody? Hard soft acid base. And what was that about? Why do we care about hard soft acid base? You know, these are little annotations you'd make in your notes sometimes. And one would be, we care about it because, you know, in MO theory, you know, we want to do LCAO. Do you guys remember LCAO? Yeah, when we do linear combination of atomic orbitals to make new molecular orbitals, we want atomic orbitals that are similar. So like a little atomic orbital and a little. Two little atomic orbitals is good, hard, hard. Or big atomic orbital with another big atomic orbital. And so we want orbitals that kind of match to make the new molecular orbitals. Let's see. And so hard soft is just simply hard likes hard, soft likes soft. That's it. And so it depends on what acid we're reacting to. Are we reacting to a hard acid or are we reacting it to a soft acid? If we're reacting to a hard acid, then oxide's better. If we're reacting it to the soft acid, then sulfide's better. Does that make sense? And we do the combination of atomic orbitals. This is molecular orbital theory. 11, an aqueous solution of 1 molar sulfide cannot be made. And that's true. Why not? Why can't we make a 1 molar sulfide solution? It has to do with the leveling effect. Tell me about the leveling effect. The leveling effect for acids is this. You know, all strong acids have the same strength in water because they all hydrolyze or they all ionize 100%. What's the leveling effect of strong bases? Yes, forms hydroxide. So all strong bases will hydrolyze water 100%. You know, strong bases, strong acids, and soluble salts are strong electrolytes. And so sulfide is going to hydrolyze water 100%. And when it does that, it's going to convert that sulfide into hydroxide. Hydroxide is the strongest base that can exist in water. So all strong bases equalize to hydroxide because that's what they're going to form when mixed with water. 12, a redox property of ammonia is that it would be an electron-rich reducer and potentially flammable. Yeah, ammonia is at the rich end. of the spectrum. And it should be potentially flammable. What is the oxidation state of chlorine in bleach? So this is, do you know the rules or not? Chlorine, when you look at the oxidation state of chlorine in bleach, what does that tell you? Is bleach a very happy chemical? Stable? Unreactive? No, bleach isn't a happy chemical. It's an unhappy chemical. Why is it unhappy? Is it because of the sodium? No. Is it because of the oxygen? No, it's because of the chlorine. Chlorine doesn't like to be +1. What does chlorine like to be? -1. So chlorine's unhappy. Meaning when I look at bleach, I think what? Automatically I think oxidizer or I think reducer? Oxidizer, right. This is like one of the household safety rules. One of the household safety rules is do not mix ammonia with bleach. Have you heard of that? You don't. And I'm not sure if this is true, but there was a manager at Buffalo Wild Wings who died, I think last year or the year before. And unfortunately, one of the reports I read was that he had mixed ammonia cleaner with bleach. And so the bleach oxidized ammonia to oxides of nitrogen, and most oxides of nitrogen are quite poisonous, you know, like NO, NO2, etc. All right, number 14. This should give 2, because we have 3 types of chlorides in this compound. 2 of the chlorides are ionically bonded. 1 of the chlorides is covalently bonded. How did I know that? How I knew that is this. Either I remembered this because we talked about this. This is what Werner won the Nobel Prize for. You know, this was an observation that just didn't make sense. You know, if you have 3 chlorides, you expect to form 3 silver chlorides. But it only formed 2. And then Werner came up with the hypothesis that the structure isn't what we think it is. In fact, when you see this, cobalt's going to have a coordination number of 6. And ammonia is a better Lewis base in this case. And that's actually typical. Ammonia is a better Lewis base than the halides like chloride, etc. In fact, ammonia is even a better Lewis base than things like hydroxide. But anyway, ammonia is going to attack first. When ammonia attacks, then there are 5 out of the 6 positions taken, and so there's only 1 more position that's for chloride. Chlorido, we call it. And so this first chloride is a chlorido. The second 2 chlorides are chlorides. Chlorido is going to be covalently bonded, whereas the chlorides will be ionically bonded. So this is part of the Nobel Prize in Chemistry here. 15. CF4 is an electron-rich and flammable compound. Can you burn CF4? No, I mean, CF4 has no electrons to give up. Fluorine certainly doesn't want to. And then carbon is in what oxidation state here? +4. It's +4 oxidation. You can't go any farther. It's already lost all the electrons it can lose. In fact, CF4 used to be thought of as an inert chemical. Inert. You know, most of these fluorocarbons like Teflon and whatever else, those are thought to be inert. But it turned out, and this is some Nobel Prize winning work at UC Irvine, It turned out that a lot of these fluorocarbons and chlorofluorocarbons, which were thought to be fairly inert because you can't burn them, they're non-flammable. Not only that, the bonds are quite strong, so they're fairly non-toxic. But but they could be irradiated with high energies of light, which breaks the bonds and makes what are called free radicals. And those free radicals end up destroying the ozone. But there's a lot of press recently for a lot of these fluorocarbon type compounds, and that has to do with forever chemicals and per and polyfluorinated compounds causing some kind of hormonal changes and this and that. And so there's a ban. California's banned a lot of these types of compounds starting this year in food contact materials, So you might have heard about the PFAS ban, PFAS. Okay, what is the coordination number for lead in this compound here? And so you'd have to know EDTA. EDTA is a hexadentate ligand. There are only 3 polydentate ligands in the book: ethylene diamine, oxalate, and EDTA. Although there were only 3, I talked about more. Oh, there it is. Here's oxalate. Oxalate's a bidentate ligand. We have 3 of them, so the coordination number is 6. Some of the other ligands that aren't in the book that I talked about, methylene diamine. Methylene diamine looks like ethylene diamine, but it's a little bit shorter, 1 carbon unit shorter. So this one's going to only form 4-membered rings. 4-membered rings are unstable. 3 and 4-membered rings. 5-membered rings are okay, and anything bigger is okay. All right, let's look at the nomenclature here. First one's the product we synthesize potassium trioxalato-chromate 3 trihydrate. And then we have the dicyanido or dicyano argentate 1. Then the tetraamine, copper 2 ion. Tris, ethylene diamine, cobalt 3. Tetraocta hydroxido iron 3. This one's carbonyl iron 2. This would be the formula for this one. Okay, then we had some reactions. The first one was metathesis. We had 2 driving forces for this: stronger acid to weaker acid and gas formation. In metathesis, the oxidation states do not change, so this is as big of a driving force as we're going to get for precipitation and that kind of stuff, gas formation, whatever. Be sodium fluoride and sodium bisulfate solutions. This turned out to be an acid base. Fluorides are base. Bisulfate ions are acid. And so this is what we end up with. So here we're going from stronger to weaker, this driving force. Next one is looks like a single replacement reaction. Some people did single replacement, but you have to be careful. If you do this as a single replacement reaction, you have to memorize the exceptions. This is one of the exceptions here where water is a solvent. There are more. There are about three basic exceptions in single replacement reactions. Instead, use the chart method. You don't have to memorize anything. And the chart, you have the chart that's given as a handout for the test. The last one is a skeleton redox. When I look at something like this, I can even see what's going on with chromium-3 iodide. The chromium this is the chromium +3, and then we have I-. One of the properties of I- is a good reducing agent. We consider I- electron rich, even though we wouldn't consider chloride electron rich. The reason I- is electron rich is it's very big. It's a huge ion. If it's a huge ion, then it's easier to steal the electron from that. And so normally when I think about iodide, I think it's a pretty good reducer. Some people did that, but they oxidized the iodide to iodine, I2, but there's no iodine in this. This is iodate. So we're going from iodide -1 to iodate. What's the, in fact, this is not iodate. You know what that is? Iodate is IO3-. IO4- is called periodate. And so we're going from a -1 to an I, and what's the oxidation state of iodine in periodate? You want to get to the point where you can just look at it and then tell. +7? +7 is correct. So we're going from -1 to +7. What's the oxidation state range for iodine? +7 to -1. So in other words, we're completely stripping. There's 8 valence electrons in the shell for iodide. We're completely stripping all the valence electrons. And so in other words, it's being completely oxidized. And so what's taking the electrons from iodide? What's the oxidizer? Peroxide. Peroxide is a powerful oxidizer. Not only that, peroxide is going to completely oxidize chromium. Here we're starting from chromium-3, and we're going to end up at chromium-6. So to go from chromium-3 to chromium-6 is complete oxidation. Hexavalent chromium. And so in other words, the hydrogen peroxide is oxidizing everything. It's oxidizing the chromium and it's oxidizing the iodide. And so here, I'm going to keep it together. Some people separated it. Normally that's fine, but this is probably easier to keep together because the chromium is being oxidized from chromium-3 to chromium-6, and the iodide is being oxidized from -1 to +7. Significant. And then the hydrogen peroxide is taking the electrons over here. But what does it form? Well, if you have hydrogen peroxide, you don't have to worry about it because if we have oxygens, we balance the oxygen first. We balance it by adding water. And so this will trip up a lot of people. So as an example, if I did plus water here, then a lot more people would get it right if I just wrote plus water, because then they can go hydrogen peroxide goes to water. If I don't write plus water here, then a lot of people get stuck and don't know what to do next. You don't have to get stuck because, if you have a hydrogen and the oxygens aren't balancing, we add water. So just add water. This is the first step in skeleton redox. And so hydrogen and oxygen containing reactants, we don't need to know what the product is because it's likely just water. So we can balance that, half reactions, Then combine the half reactions here. All right, any questions on this? No? All right, remind me where we left off last time. What were we talking about?
We're doing delta G for the evaporation of water.
Okay.
And we started talking about one of the versions of the Clausius-Clapeyron equation.
Did we already calculate the boiling point of water at 1 bar?
Yes, that's what we did last.
Yeah, that's what we
Okay.
finished off.
So it was off a little bit. All right. So we use the Clausius-Clapeyron equation to calculate the boiling point of water at 1 bar. And the boiling point, which is the temperature, was 99.5 degrees C. Is that correct? It was just a little bit lower because the pressure was a little bit less, so it didn't require as much energy to boil. What was our calculated boiling point? The calculated one was like 97
At 1 bar,
at 1 bar,
it was 99. Oh, it was 97.
yeah. 97. Okay. 97.08. So it's still off a little bit, and what we're going to do is we're going to account for this difference. The difference is due to probably our assumption. What was the assumption that we made?
The delta H and delta S were at 298.
Yeah, the ones that 298 were applicable to here, which is closer to 372, 373. That's probably off a little bit. But nonetheless, it came out reasonably close, so we'll just say fairly close. Values. We did have the data. And so that was changing, we were looking at changing delta G under standard conditions by manipulating the temperature. And so delta G naught at temperature T is equal to delta H naught at temperature T minus T delta S naught at temperature T. So if we can change the temperature, then we can change the driving force. And in fact, we could reverse the driving force. And so this is what we were doing in this case. The driving force was positive, delta G was positive. And then we just set the delta G equal to 0 and then calculated the temperature, and that gave us the transition between positive through 0. And if we keep going, we'll go negative here. Unfortunately, we didn't have these, so that was the assumption we made. The assumption we made is this is going to be close to delta H at 298 minus T delta S at 298. These are all under standard conditions. Okay. So we want to think about things. Let's take a step back here right now and think about these. We want to think about calculations. We're going to be doing a lot of calculations. So, for delta H, do you know all the ways to determine what delta H is? How can you determine what delta H is? Tell me the easiest way to determine what delta H is. Delta H for a reaction or process. What's the easiest method to determine delta H? Let me ask you. Bomb calorimetry? Is bomb calorimetry the easiest way to determine delta H? Does bomb calorimetry even determine delta H, or does it determine delta U? Delta U, right? If you wanted delta H, you probably shouldn't use bomb calorimetry. You should use coffee cup calorimetry, right? But I probably wouldn't do it. I wouldn't do bomb. I wouldn't do coffee cup. You could do bomb and then correct it, mathematically. But why do all that work? The easiest way is what Edgar mentioned. The easiest way is to use Appendix D. And so the easiest method is, we already did it, right? We use the delta H's of formation. Then we're going to go to delta S. What are the ways that we can determine delta S? Well, the easiest is if we restrict it, just like delta H. We have to restrict it because this is going to limit delta H. The only delta H we're going to get is the delta H at 298 because Appendix D is at 298 and under standard conditions. And this was the sum of delta H is the formation of the products under standard conditions minus the sum. This is nu. This is the number of moles. Delta H is the formation of the product under standard conditions. What about delta S? Well, delta S is kind of in the same boat. We can calculate delta S, 290 Kelvin. The easiest way is just to use Appendix D. We use Appendix D, we're going to just sum up the absolute entropies of the products minus the sum of the absolute entropies of the reactants.
Delta H, you put products twice.
Oh, thanks. Should be reactants. There are other methods for determining delta S. So, for example, it turns out that this is delta S. This is not S. If we're looking at S, we could use like the Boltzmann equation. But here, delta S is related to Q reversible over T. Did I talk about that? It's related to how much heat is exchanged at a given temperature. And based on this, we can get some additional relationships with this. One of those is this, the delta S at a phase transition. A phase transition would be like boiling, freezing, etc. There's really some change in state. So delta S at the phase transition is just going to be delta H at that transition over the temperature. So an example would be like calculating the boiling point. We could try to calculate the boiling point. the temperature of the phase transition, the boiling point, is equal to delta H of the transition over delta S of that transition. This is a calculation we just did. It turned out delta H is 44 divided by 0.118 delta S. Twice. Some others involve some calculus, called integral calculus. These calculus ones, the derivation's kind of beyond the scope. I mean, the book does some work trying to derive these. So we have delta S in a phase transition. We can use this. The next one will be delta S and a temperature change. Delta S and a temperature change, we have the equation here. Show you. So we use some calculus to come up with it, and we come up with this equation here. You know, we see that delta S, sorry, is related to Q. Q is also heat under certain conditions. So Q over T, Q reversible over T. And so what we do is, when we do a reversible change, we try to do it infinitesimally slow. When you do it infinitesimally slow, then we use a little bit of calculus and we come up with these types of equations like this. So this is delta S in temperature. If there's a temperature change, we can calculate the entropy change. So let's say we heat up water. You know, if we look at Appendix D, we're only going to get the entropy of water at 298 Kelvin. But let's say I wanted, what is the entropy change of heating water from, let's say, 25 degrees C to 100 degrees C? You know, how much did the entropy change? Okay, so what we're going to do is we're not going to derive this equation. We're just going to use this equation. And we're going to plug in the absolute temperatures here, 373, 298, initial. And then we need CP. Do you know what CP is?
Constant pressure.
Constant pressure, yes, but what is the P alone is constant pressure. The C doesn't stand for constant. The C stands for heat capacity. This is the constant pressure heat capacity. The constant pressure heat capacities you can find in Appendix D. Appendix D. And so we could get that from Appendix D, but the heat capacity changes a little with temperature. And so what we're going to assume is that the heat capacity doesn't change with temperature, but that change with temperature was what we were using to determine experimentally what the absolute entropies were. So we have that. So that's delta S and a temperature change. Okay, we can go on to delta S and a temperature and pressure change here. So if we have both, then we just add them together. We add the entropy change with temperature. This is the entropy change with temperature here. And then we add to that the entropy change for change in pressure. Now, our book's author does not like to invert this here. So P final going on the bottom, P initial going on the top. So normally it's P initial over P final. And so What the authors did was they flipped it, and then they could change the sign. But it should be the entropy due to the temperature change plus the entropy due to the pressure change. But it looks like it's minus. It's minus just because they flipped the sign there. I'm not going to flip the sign. And so let's go ahead and let me write this down here. And so the delta S due to the temperature change, we could just write as is here. So you don't have to memorize any of these equations. It's Cp ln Tf over T initial. All right. Delta S due to a pressure change. So let's look at delta S. Delta S due to a pressure change is just going to be NR ln P final minus P initial. This is the way they had it written in your book, so it's a minus here. Or equal to NR ln P initial over P final. Then we don't have to change it. Yeah. But it doesn't match here. This is final over initial. This is initial over final. Now, if we do a temperature and pressure change, we just add the two terms up. So we do the entropy change due to the temperature change plus the entropy change due to the pressure change. See. What if there's a volume change? And so look at the entropy change due to a volume change. This one I'll say a few more words about. If there's a volume change, let's say the system increased in volume. So the system started off with this volume and then expanded the volume. Okay. So expand the volume. If the volume of the system changes, was there work done? So let's say this is an ideal, these are all for ideal gases, by the way. Ideal gases. Let's say the temperature starts off at 298 Kelvin and the temperature ends at 298 Kelvin. In an ideal gas, there's only kinetic energy. In an ideal gas, there's only translational kinetic energy. This is going to be related to temperature. And so when we look at the energy here, there's no potential energy, it's all kinetic energy. And the kinetic energy is going to be related to the temperature. And the temperature is a measure of the average kinetic energy. And so if we start off at 298, we end up at 298, the average kinetic energy did not change. We both are at the same energy. So energy didn't change. Was any work involved? Well, when you increase the volume, let's say the system increases its volume, is any work done? Yes. Who did the work? Let's say you blew up a 10-liter balloon. Was any work done? Who did the work? Well, you did the work because you blew up the balloon, right? Is that correct? So this is what we call isothermal. Do you guys remember isothermal versus adiabatic? Yeah, Tristan remembers. Anybody else remember? What was isothermal?
Constant temperature.
Constant temperature. Adiabatic? Not constant. Adiabatic just means that
No work was done.
no energy is exchanged between the system and surroundings in the form of heat. Does that make sense? So we could do we can do an isothermal expansion of an ideal gas versus an adiabatic expansion of an ideal gas. That's back in chapter 5 or whatever. Not chapter 5, chapter 7. If we do an isothermal, then what happens is the temperature stays constant. But have you ever used one of those the gas cans to clean the keyboard, compressed gas? You know, when you use that, the can gets really cold. The can gets really cold because when we expand a gas, work is done. If work is done, then the work requires energy. And so where did that energy come from? The energy came from the surroundings. So the surroundings are going to get cold. And so here, this is isothermal. And so the work that was done in expanding the gas here the energy for the work required to expand the gas is going to come from the surroundings. And so, do you guys remember the equation for work? PV work? It's minus P delta V. Do you guys remember that? That's the amount of work. And when we look at this, the entropy here is going to increase. And all this is going to come from Q. You know, the surroundings are going to get cold, basically, to maintain the temperature here, let's say. Or colder. And this is going to be related to delta S. And so here, if we use some calculus, this is what we're going to do. We're going to do infinitesimally small volume changes. And so infinitely small volume changes. And we're going to use some calculus to do this. And then we're going to come up with this equation that delta S, which is going to be the usable work, right, that's going to be done in this S, is going to equal this N R ln of V final minus V initial. Since pressure and volume are inversely proportional, then the pressures are, you know, as the volume expands, the pressure decreases. As the volume contracts, the pressure increases. So they're inversely proportional. So we get the same equation. It's just that pressure and volume are inversely proportional here. And so if there's a volume change, we use this. If there's a pressure change, we use this. If there's a combination, we just add them, you know, to get the total entropy change. All right. So these are kind of different ways of determining delta S, but probably the most common way that we're going to use is Appendix D data, and that's going to be the easiest way to determine what delta S is. But it's also going to be limiting because Appendix D restricts things. Okay, so those are ways of dealing. So different calculations for different scenarios here. Now, what we're going to do is we're going to move on to delta G. Although let me say there's one other way. You know, we could have delta S, which is the S final minus the S initial, and then we have the S is equal to K, the Boltzmann equation, K ln W. But this is difficult to calculate the absolute entropies based on the ways of arranging microstates. It's not so easy. So what we're going to do is move on to delta G, and we're going to try to think of all the ways of calculating delta G, and we want to get familiar with all the ways for calculating delta G. And so that's what we're going to do next, but we're out of time for today, so we'll look at this next time on Monday. On Monday, I'm probably going to finish this chapter, I think. We'll do a few calculations afterwards. But